Okay, well, again, yeah, it's incorporating geodatabases into a workflow. So QPS provides software solutions for the maritime community, and in specific, looking at acquisition of maritime data. So this could be, for instance, for this application would be bathymetry or seafloor imagery data and things like that. And we do that through the Quincy software solution. And then recently we've launched a product. It's a 3D hydrographic data processing engine for the data processing of multi-beam data in specific. Then we bring that into a visualization analysis space with Fleeter Mouse. And then we also have a couple other solutions with Castor and Castor Connect, which is navigation, docking, and data distribution. For this specific talk, we're talking about bringing in and evolving these solutions in with the Esri workflow, and both the back end and the front end. So in general, ocean mapping has evolved, in technology. We've watched that technology evolve enormously over the past couple hundred years. And I always look at this like, oh God, I used to think I had it hard when I was working on a ship, and I see these guys out there just dropping a lead line day in, day out, and I think my God, that hurt my shoulder after a while. Then we evolved into ocean acoustics, specifically, and started off with single beam echo sounders. The problem with single beam, though, is it just gave you a slice of a cross-section along the seafloor, and you're missing a lot of information in between. And then some really smart people came out with a multi-beam technology, which basically casts a swath of sound across a broad area to give you full three-dimensional visualization of the seafloor, or acquisition of data for the seafloor. So with that, we've moved in and enormously improved our ability to see what's going on, and in a variety of different aspects. As multi-beam technology has also evolved, we've been able to extract more information. So we started looking at the ocean acoustics themselves, looking at the seafloor return intensities as well as in the water column as well. And so we started off looking at just, what we call fetching two beams on either side of both the port and starboard sides of the sonar, and basically gave us a side scan-like image, so like a black and white image giving us roughly how hard the substrate is on the seafloor, whether it's sand, rock, etc. And then that evolved further down the road, and we were able to look within each beam. So multi-beam means various beams, so you can go anywhere from, I start off with 101, now we're up to 500 to sometimes even more now beams per ping. And within each beam now, we're starting to look in, and it contains a lot more information, and specifically looking at the amplitude value associated with the bomb detection sample number for each beam. And then we're able to basically get what we call backscatter out of that information. Again, gives us more detailed information of the seafloor hardness itself. And then we started going, I remember thinking about this back in 2000, and a lot of us were thinking about it back then. It's like, well, God, I know I'm out on survey and I see these things popping up in the water column. I wonder what it would be like to be able to look at that. Because current bioacoustic studies are just giving you a slice of the seafloor, or a slice of the water column, similar to single beam echo sounders of the sea bottom, but we're looking at the water column. And, and this is actually data that's processed by Dr. Tom Weber at the University of New Hampshire. And, and we were missing this entire fish school. All we were getting was that slice. So incorporating the water column information was giving us a lot more information than, than we ever dreamed of. And then we started looking at in different applications, looking at seafloor seeps and things like that, and on the coming off the seafloor to help us for oil and gas exploration, or even for scientific applications, trying to identify methane seeps and black smokers and things like that. Then suddenly we have this plethora of applications. By looking at all the different data types, incorporating all the different resolutions, we now could use it for dredging applications, which is probably the most common application out there, and incorporates well over 50% of the multi-beam market itself. Mapping, just for straight hydrography. Defense and security applications. I'd love to tell you how many applications are there, but I can't because it's all confidential, right? The energy sector, so looking at both not only from a ship-based system, but from remote operated vehicles, autonomous underwater vehicles, looking for pipeline, catenary work, metrology, exploration. And then research, there's also a plethora of applications, including habitat classification, looking at midwater tracking, and again, exploration. And these applications just seem to continue to grow over time. And with this, though, the evolution of GIS has come with hydrographic applications. So my first habitat mapping project I worked on was back in, I want to say 1993 or 94. And back then we were collecting all analog data, so paper records for side scan. And we would literally we'd take the strips, cut them out, we'd lay down this grid, and then actually we'd have the track lines as well and use events. And the term mosaic came from you're literally mosaicing the side scan imagery together based on adjacent strips of paper. And then we would take a Mylar overlay, lay that down over the side scan, then we'd start taking our colored pencils out and drawing polygons around different seafloor habitat types. And then we would further refine that and keep that going. And then we would color code it. And this was where I had my first introduction to GIS, was using ArcInfo. So then I would have to hand digitize this over a large digitizing tablet to bring this into the GIS system itself. So we look at the evolution of this and how this has changed over time, and now we're able just simply to take all of the digital information and get a variety of different products out of that in one go and bring it directly into the application and look at it not only in 2D, but in full 3D as well. So in short, we've really evolved from just trying to, have one person that's trying to make a variety of different connections, and it's very, labor intensive, to, okay, let's move more towards an analog to a digital world. And this is funny, actually. This is actually a picture of my dad's actual phone he had in his car. So I would love throwing this into talks. And it was like $5 a minute. And you'd be like, Chris, get off the phone. But now we have things that are quickly in the palm of your hand. So the evolution is really, all information is right there in front of you. We could access this at any time. So now we're looking just in the acquisition of hydrographic-based data, and what is required. Okay, so it all starts with a data acquisition system. So for QPS, that would be our Quincy acquisition system. Then we have to bring in time. Time's probably the most important thing because everything needs to be time tagged. Your position, your heading information, your pitch, roll, and heave, your tide information, your sound velocity, going straight in from the, and then sound velocity at the head, the sonar head itself, that's connected to a sonar processor, the receiver, and the transmitter or the sound source. So there's quite a bit that goes into it. And all this is mounted on a ship that is constantly moving on sea. We're trying to locate with satellites up there and bring this all together to form a nice, pretty three-dimensional image of the seafloor. Is this our new solution? Is this where we're moving? This is kind of where I'm hoping we go. What does your modern day cell phone have to offer with this, right? So we have the time. We have our latitude and longitude, our position. We have our heading. We have our motion, because all these have MEMS motion sensors in them now. We have our tides. And then there's actually even a sonar app you could download off of here. And then, of course, you have the GIS all into one system. But we're not quite there yet. Because even with all these technological advances around us, the seafloor mapping is still extremely hard. So many of the frustrations that we're dealing with is we're dealing with a human operator that still needs to make all the connections to make on-the-fly decisions and come up with a final solution. And this is true even for experienced users. Mistake happens, we try to put safeguards into them to catch them, but mistakes are fixed and sometimes at great cost and great price. And it happens again and again and again, project after project. So within the data acquisition area now, we're starting to look at bringing in ArcGIS during hydrographic operations themselves. And we start asking ourselves in real time as the survey is going, because when you're out on a boat out in the middle of Alaska or wherever you're out surveying, is that these decisions have to be made often on the fly. And so it's nice to be able to have access to your GIS system in real time. You could ask yourself questions such as, where the highest resolution data sets are currently available for me in the Gulf of Mexico, for instance. Where do I have old data or low quality data? Because do I really need to go and survey there? And what did my seabed look like 10 years ago? And so I can compare it and see if there's any changes on there. Is there a high spot now that suddenly wasn't there before? And can we combine all the data sets in the harbor now that currently exist within this GIS system to make sure that old data sets don't hide the new ones? And then also, can you just show me from sensor X? Because I think I may have a problem here. So all this now can be done in near real time. Oh, come on. There we go. So this is where we bring in. So rather, we used to talk about we've been talking about this for quite a bit of time, and some of you may have seen talks on this, which is the QPS Esri workflow. So we have the acquisition, the processing, visualization, analysis, then into the Esri for maritime or the BIS systems. So now we're talking about sandwiching it. I'm currently calling it the QPS Esri sandwich. And so we could bring this into the front end. So here, it's an iterative process. We can actually make queries in real time. And this is being used by a combination of people, mostly in the dredging right now. And the other one I'm most familiar with is Clearwater Seafoods, for instance, up in Canada, are connecting to the geodatabase in real time. And when it comes to iterative process, you can make decisions on the fly. So this is general. So when you're out surveying, there's a lot of information too that's at your disposal. So to be able to make these decisions on the fly are nice. The most common display is the general navigation display. So if you're doing hydrographic applications, it's nice to be able to tie the geodatabase in with the dynamic service to give you the depth and shadow in just information, so basic bathymetry. And then, are we within our 98% confidence level of the data set themselves? And then we could also use it to tie directly into, say, fisheries. So this is where the applications start to get even more interesting, is we could look at the catch information and say, okay, this is where we want to go survey right now because we need to know what the habitat type is there. And then looking at dredge under and over depth. So we could bring in prior TINs that were created and bring that straight into Quincy, into the data acquisition systems, to make sure that we are within the requirements that are set by whatever port we're working with or whatever agency that's writing the requirements for the dredging. But despite how much planning you do, regardless of application or data types, this is still extremely complicated. So this is a total propagated error slide, and I've stolen this from off of somebody else's presentation that borrowed it from Brian Calder. And Brian's at University of New Hampshire, and Brian's quite famous for the cube algorithm, which is being used for a lot of the area-based processing of multi-beam data. But if you look at everything, I mean, we have the sound speed information and all the different roll, pitch, and heave measurements you have to deal with, the depth, and all this just to get at one value. So it's not an easy process. As much as I'd love to be able to do this straight from my cell phone, we're still there and we still have a lot of decisions to make. And unfortunately, the majority of errors that are made are usually due to humans. Just like total propagated uncertainty or TPU, human error can compound with each mistake, and often at great costs. So you may have great measurements, but your deliverables may not reflect all that effort you put into it. And potential outcome too is you may have great result, but it took a long time and a lot of people and a lot of money to get to it. So that's why being able to make decisions during your survey and at every stage is, and have access to prior information or as much information you can get is critical. So, samples of the sources of human error. I mean, just the sign convention. So looking at X, Y, Z. Some people think X is in the stern, bow direction, stern out, and then or X, Y, or the port starboard. So or positive negative switch. I mean, these are constant areas where we haven't really come to a common decision how we want to use it. But as long as we're able to keep track of these things, then we can account for them. But unfortunately, typos happen. People get tired. They've been out on a ship. I seem to get the honor of working the graveyard shift, so after my 12 hours, I'd be tired, and and that's when mistakes start to really slip in. Just importing ancillary data, so your SBETs and things like that, or tides, and failing to apply it correctly, these could also create problems. Changing processing configurations and not triggering the appropriate reprocessing. Then not triggering the appropriate reprocessing for files that need it. And then we try to come up with these checklists, but I'll be honest with you, at the end of a 12-hour shift, I would get that sheet and I'd be just like, okay, I'm really hungry. I just want to go to bed and just be check. Did I do that? I think I did. Yeah, and move on. And I warned the guy before me. I was like, I'm not sure because I was a little tired at the end of the survey. And, but you can see here, somebody started typing snippets versus what actually the line number was. So, a lot of these things can happen during. So what if there were a solution that automated the mundane and error-prone tasks for which computers are well suited for, but humans aren't? And we isolated the stages for which humans bring value to the process. For example, data validation, so knowing the good from the bad. Processing configuration and management, so you're managing the recipe but not the process. Then troubleshooting, so identifying causes of errors. And then we integrated this all in within the QPS Esri workflow during the processing stage. and say, oh yeah, I think we got one. And this is what we've recently introduced, which is Qimera. So it does all that, plus it performs the complete hydrographic processing for most modern sonar formats, many ancillary formats for SBETs, POSPAC, most tied in SVPs. Then of course exports that include, for instance, the bag format and other image formats that go over into the Esri GIS. And this, we create that link to the ArcGIS to assist in the processing decisions as well. So Qimera Innovations and things like that we're working on, it's a guided workflow. So it lets non-expert users write at a typical bathymetric deliverables with little training or expert knowledge, or very tired surveyors as well. It guides you through the process. And then also a dynamic workflow, so processing state management. We codify and manage relationships between observations and the results. So you don't need to remember what processing needs to be done, just that some processing needs to be done. And in short, Qimera keeps track of what you're doing and does all the math for you. So when you're tired, or you don't have that much training and you've been thrown into this survey, it helps you get there. So what's a guided workflow? This was actually shot by my colleague Jonathan Bodewin, and this is classic. This is Akira. You can find this in every hotel room now. And it's pretty simple. You hit the green button, you press another button, it pretty much tells you, okay, I insert the coffee now. You close it, then you put the water in. I will not lie, I have put the water in where the coffee pod was supposed to go. But so it's simple, then you close it, and boom, you have your cup of coffee. It's that simple. That's a guided workflow. It tells you what to do, so you really not much thought process has to go into it, just that you need that coffee because you just got up. So the Qimera guided workflow works similar. So what happens is you start up the software, and the first thing you see is it asks you whether you want a new project or you want to open up an existing project. You say, I want to create a new project. And then you name that project, it tells you where it's going to go. You don't, and then if you're using, depends on how you collected the data, but it'll choose a projection based on the source files itself. So you have very little thing. You don't have to assign this. It'll look at what's stored in the data and create that for you. Then it simply says, do you want to add raw sonar files or point process? You say yes. Then it just will automatically load this data up for you. Asks you, do you want to create a dynamic surface or a gridded surface that you can look at? And then you set your resolution. It actually has a suggested resolution for you, so you could go ahead and just keep moving down the line. And then, boom, you have a map. You're ready to start processing data. And 5 clips later, you have the map. You're able to start processing. It's literally that simple. And hopefully, I know some of you in the audience were at the talk yesterday. Actually, probably would have been nice to go through this earlier, but you could, live, you could say that, yeah, it really was that easy. And then we could also, the nice thing too about Qimera is that if you make a mistake or you could validate your data immediately. So for instance, I was going through and I wasn't really paying attention to what I was doing. I clipped out this entire area. Then I looked in the 3D model, and yep, sure enough, it took it out. Then you could go back and say, okay, I want to undo that. Simple little undo button, and you put it back in. So much like we had this iterative process at the acquisition end, Qimera does have a way to be able to move straight over to a bag surface. So if you don't need to move, if you're ready to move straight to charting, don't need to do visualization analysis, Qimera allows you to create that link through the bag surface itself. If you have information you want to bring back over to help you assist in your processing decisions, you can bring it in through the shapefiles or grids and whatever, in a variety of different formats as well. So we create that link at the processing stage to go straight over to the charting or to the BIS if needed. But more common than not, more questions come up, especially if you're working in habitat type related situations or oil and gas exploration, and it's like, okay, how does seafloor backscatter, for instance, correlate to slope? Do water column anomalies correlate to the seafloor features? Because we are collecting now, we're working on a plethora of applications, a plethora of different data types, including water column. And how does the geomorphology correlate with rugosity? Wouldn't a movie be really cool right now? Like, I want to create a fly-through and see how this looks. So at this point, we have the Fledermaus end of it, which is our visualization analysis package that creates a direct link with the Esri ArcGIS itself. So Fledermaus will bring in third-party data. You can bring in the Qimera vector data, lines and points, raster information, the Fledermaus analyses that can be conducted, so such as rugosity, slope, BPI, or FleetMouse-derived products, such as the vertical curtains or water column and backscatter data. And with that, we create this bidirectional link with the Esri GIS. And the nice thing is you can work with Soundstage directly with the ArcGIS workspace, so it's connected directly. And then within, and basically any attribute that is within the ArcGIS, within the FleetMouse, also we have a direct tab in FleetMouse to connect directly with the ArcGIS. So that's a nice bidirectional link. So now we're in the into the GIS. Many of you probably know this a lot better than I do, so I won't dwell on it too long. But the first challenge we address now is probably the most important: is the data is traditionally locked. We can bring it in, and just basically making the GIS enabled. So within the QPS Esri workflow, we're now defining to be able to access at any point your bathymetric data and share it via your GIS. Again, just bringing back, so we using Quincy now on the front and back end, Qimera with Esri input and output, and FleetMouse directly to the Esri. So just to kind of summarize, where we're at here, the evolution of technology for hydrography-based applications now brings us to the integration of not only sensors, but creating vital links between the technologies. So at the planning stage, again, we're using the geodatabase. So what questions need to be asked, and where do we answer those questions? Real-time decisions can be made during acquisitions. Where was the last dredge conducted, for instance? Are we over or under depth? Is my data in line with what we saw in the past? Are we fishing in good catch areas? Are we even surveying the right data? Do we need to collect additional data in this area to make sure that we are fishing it efficiently? Then the guided workflow during processing. We're reducing mistakes through automation and guidance, and the math is being taken care of. Then, of course, we're creating that most important, but that bidirectional link with Esri during visualization analysis and chart production. Providing a 4D dynamic visualization analysis environment where allows integration of the GIS tools and then helps prepare for final production of hydrographic-based products.